Hey there, Math 2403. Welcome back to Unit 6, Video 4 of 4. Today we will be continuing on with our confidence interval and hypothesis testing unit. Today's topic is hypothesis test for the mean mu. We'll only discuss the case where sigma is unknown, the more practical case. So we'll be relying on the t-distribution. This should seem pretty familiar. We'll be using the same 8 steps that we used for other hypothesis tests, like when we were doing a hypothesis test for the population proportion earlier. Let's get right to it. Testing claims about the mean. We're only going to do the case where we don't know the population standard deviation. When we were doing confidence intervals, we did do the case where sigma was known and we use a z distribution. And when the standard deviation is unknown, which is the more realistic or practical case, we'll use the t-distribution. Basically, to conduct a hypothesis test for a mean, we'll have the same requirements that we had to do a confidence interval for the mean. Basically, we need our sample to be random. We need to have a sample size that is either big enough, greater than 30, or we need to know that the population is normal to begin with. Once we know that, we know our sample means will be distributed normally, but we'll have to use a t-distribution to tweak things a little bit because we don't know what sigma is. So the central limit theorem doesn't apply perfectly. We do this little adjustment using t with n-1 degrees of freedom. So we already know how to read the t-table. We already know how to calculate a t-score. So basically we just need to apply this to our 8-step formal procedure for hypothesis testing. So we pretty much can just dive into an example. We'll just make sure that we abide by these conditions, and we will use this test statistic and distribution. Here's an example. We have some drill bits, and we tested 35 of them. The mean time to failure of our 35 bits under certain controlled conditions were 7,340 hours, and the standard deviation was 870 hours. Basically, we did an experiment where we had 35 drill bits. We tested them for life, and we found that our 35 bits lasted on average 7,340 hours with a standard deviation of 870 hours. The company who sells these bits claims that the drill bit life on average is longer than 6,950 hours. So that's their claim. Step 1 is that the mean life is longer than, so say greater than, 6,950 hours. Basically, we're going to compare our sample result to our claim. Step number 2, to do this, we'll have our null and alternative hypotheses. Because this claim does not have an equal sign in it, it will have to sit in the alternate hypothesis position. So alternative hypothesis is mu greater than 6,950 hours. Our null hypothesis is then just the opposite. So we're basically going to assume the opposite of the claim is true throughout our, analysis. Step 3 is where we pick alpha, and just to shake things up a bit, let's let alpha be 0.10. or 10%. So there's a 10% chance we're going to reject this null hypothesis, even though it's already true. In the real world, if rejecting the null hypothesis when it's true leads to, someone dying, has very great consequences, or it costs a lot of money, then you might want to have a lower alpha so that you have a lower chance of making that mistake. But if making that mistake isn't that big of a deal, then you can get away with having a higher probability, knowing that you then have reduced the probability of failing to reject this when it's false. Which maybe that's the dire problem, and if that's the case, then you would want this to be a higher value. But generally, we don't go much higher than, say, 10%. Step 4 is where we check our conditions. Nowhere in this description did I see anything about sigma. I put the word standard deviation, I actually put it in words there to, try to trick you, but it said the sample mean of 35. Well, this must be the sample standard deviation. So this is S. Sigma is unknown. Which makes sense, since if we don't know what the mean is, how do we know what sigma is? N is large, so we don't even care what the distribution is. We don't need to, construct some sort of normal probability QQ plot to determine whether these 35 values are normal or not. Basically, the central limit theorem says, well, as long as we're over 30, we're good to go. But because we don't know sigma, we'll use the t distribution for the distribution for our sample means, with n minus 1 degrees of freedom. Step 5 is calculate the test statistic. For this guy, it's just a t-score, x bar minus nu, s over root n. Our x bar is given above, 7340. Our mean is the null hypothesis. Now, we're assuming that the mean could be 6950 or less, but the closest call between the null hypothesis and the alternative will be when it is 6950. So let's use that. And if it works for 6950, it will work for anything smaller than 6950. Our S is 870 hours, and we did a sample of 35. Calculate this t-score, and I get 2.65. A little bit, somewhat large maybe. But remember, we don't want to just judge this as being large or small for t-score, because we have to remember that when you have a one-tailed test, sometimes unusual isn't that unusual if it's, on the right side of, your tail. So let's figure that out in step 6. Step 6, we have the two methods. We have the traditional way and the p-value way. I'll do traditional and p-value. Again, you would never do both at once. Just trying to teach you both methods. Is this a two-tailed test? One-tailed test? If it is one-tailed, which direction is it? We'll take a look at this thing. The null hypothesis is that the mean is less than or equal to 6950. So values of even a weird value like 5 hours wouldn't disagree with this null hypothesis. The only way we would disagree with this null hypothesis is for values that are much larger than 6950. So this ends up being a right-tailed test. Basically, look at the alternate hypothesis and check which way it's pointing. HA points the way it's pointing to the right. So if we're doing a right-tailed test, we only have one critical value. It's a t-score in this case, and we'll write t with a subscript alpha, where alpha is the area underneath the curve to the right because we're doing a right-tailed test. And we know that that alpha in this case is 10%. And now we just need to figure out what this t-score is. What t corresponds with an area of 10% when the degrees of freedom are 35 minus 1, which is 34. So we're going to look in our t-table under 34 and alpha is 0.1. Let's take a look at that. This is my z table, and here is my t. I'll erase all this previous stuff that we had going on from some previous lecture. And now we know that we're lucky, this problem is to the right. So our t-table is to the right, remember? We're looking for 10%, and we're in the row for 34 degrees of freedom. So we get 1.307. That's our critical value. Let's go back. So from the table, this cutoff value is 1.307. Anything to the right of 1.307 is in the rejection region, which our value is. Our test statistic of 2.65 is up here somewhere, on this t-axis. So this is strange, we will reject the null hypothesis. Step 7. Our test statistic is in the rejection region. So our conclusion will be reject null hypothesis. You see how we're getting faster at doing these now? Step 8 is our conclusion. And remember, we had a handy chart for this. Our decision here was rejecting the null hypothesis. And our claim was HA. Let's go and look at our chart. Our decision was reject the null hypothesis, and our claim was in HA. So here's our wording. We can say that we support the claim. Rejecting the null hypothesis in this case means that we're supporting the claim. And we have a quantification for, the probability of our error. So we get to say it fairly strongly. The sample data supports the claim. Is nice, strong wording. I like to always add in the alpha. The sample data supports the claim at alpha equals 0.10 that the mean drill bit life is longer than 6,950 hours. Again, this one makes sense. Somebody claims drill bits last longer than 6,950 hours, and you did a test and got 7,340, you do pretty much agree with them. So we've turned this into this big formal thing, but you probably would have agreed with them anyway. It depends on how close it is. Like if this number had been, 7,000, do you necessarily believe them? Well, yeah, it still feels pretty good. When you end up lower than it, if it's a lot lower, then for sure you would reject it. But if it's not much lower, you might still agree with it. So don't completely lose sight of, your common sense here when you're viewing these. It's easy to get wrapped up in the steps. If you're a Excel person and you didn't like looking this up in the t-table, I guess that's a t-score. So we would say t dot. We know the probability t dot inv to get this value. And we could, if we're doing, I think there's a t dot inv to the right, but I'm not sure. Like usually our inverse function, almost all of our functions go to the left. So I know that if I do t dot inv 90% with 34 degrees of freedom, I'll get that number. I'm not sure if there's a t dot inv dot right. If there is, then you could put 10%. I'm not sure about this function. They added some functions to Excel in more recent versions, so I'm not sure if right was added to the inverses or not. But for sure, going to the left the traditional way, the traditional cumulative way should work. If you didn't like this traditional method and you like p-values better, you would have written, p-value method and right-tailed. And then we would have just found the area to the right of 2.65. This is our p-value. Of course, with the table, this is really hard to do actually, because 2.65 is probably not going to be in the table. So the best we can do is sort of, find a range that this probability is. I'll show you. If we go to our table and we're in row 34, we're looking for the number 2.65, but it's not in the table. Because there are so many t-tables listed here, we can't list all the values. It's not as good or easy to read as the Z table. Our t-score is somewhere between these two values. So that area is somewhere between, 0.5% and 1%. So even though I can't get it exactly, I know, in the ballpark. So from the table, the best I can say is this area is somewhere between 0.005 and 0.01. Or I know that there's a right for the tdist function, t.dist.right. And we'll just go to the right of 2.65 with 34 degrees of freedom. And Excel will give us the value. In fact, it turns out to be 0.006064. And you can see that that number is in the range that we predicted it to be in. The nice thing is being in that range means that you are smaller than alpha, even if you don't know what it is. Alpha was 10%, so we know that we're under 10%, even if we don't know exactly what it is. So our conclusion is p-value is under alpha, so we reject our null hypothesis. And then we can write our conclusion just as we did. So personally, I prefer the p-value method. Especially on a one-tailed test. On a two-tailed test, you might as well do a confidence interval. As we saw when we did confidence intervals in the homework, if the tested value, if the null hypothesis ends up within the confidence interval, then you tend to not reject the null hypothesis. If the claimed or the null hypothesis is outside of the confidence interval, then you do. So you can actually do a formal hypothesis test using just a confidence interval if you know that it's two-tailed. But on the one-tailed version, then you have to resort to this. Do one more quick example. Hopefully we can get quicker at these as we go. Maybe we won't do both methods to speed it up. We have a beam and we're applying a load to the center of it, and then we're measuring the deflection. And we're just putting the same load each time to, I guess, similar beams. So we have, how many times did we do this test? Only 10 times. So we tested the deflection of 10 different beams with a 100 kilogram load applied to their center. And now we'll do some sort of test. Someone must make a claim here. A building technologist is claiming that the deflection of a particular 4-meter timber beam is 0.150 decimeters. Okay, that's their claim. Step 1. The mean is 0.150 decimeters. Step 2. Set up your null and alternate hypothesis. And by set it up, I mean decide where to put the claim. This time the claim has an equal sign in it, so that means it's the null hypothesis. And the alternative is that it isn't 0.15 decimeters. Step 3, pick an alpha. Oh, look at that, I did 0.1 again. Type 1 error has a probability of 10%. There's a 10% chance I'm going to reject the null hypothesis, which in this case is the claim, even though it is true. Step 4, check our conditions. Sigma is unknown. We have no idea what sigma is. N is tiny. It's way under 30. We only did 10 tests. So we could be in trouble here. When you have a small sample size and you don't know what sigma is, you might not be able to do it at all. You need one more thing to be true. You need this data to be normally distributed, or at least roughly normally distributed. And it's really hard to tell if data is normally distributed when you only have 10 values. So hopefully we know something about the situation that would make us believe that, yeah, this data should be normal. And in this case, it told us. We may assume that under these conditions that we have normal distribution. So, but the distribution is normal. So our sample means will follow the t-distribution with n-1 degrees of freedom. Now we can do our step 5, which is our test statistic, x bar minus mu, s over root n. In order to do this, now I need to punch these 10 numbers into my calculator. You know, get your calculator into stat mode, or use Excel if you have it. Punch those values in. Our mean turns out to be, from my calculator, I get 0.417. Sorry, 0.1417. And my standard deviation turned out to be 0.01525 decimeters. So from this sample data, we have x bar and s. And now we can calculate this thing. 0.1417 minus what we're assuming it to be, 0.150. Divide that by our sample standard deviation of 0.01525, and divide that by the square root of the sample size. In this case, there are 10. I ended up with a value of negative 1.720, which is a little weird, but not that weird, especially given the small sample size that we have. I bet we're not going to reject the null hypothesis. Well, let's check. Step 6. Maybe we'll do the traditional method. This is a two-tailed test. HA points the way. Well, it sort of points in both directions. If you're not 0.15, it means you could be bigger or you could be less. So we'd have two critical values, a positive and a negative. We'll have our alpha split in half. Our degrees of freedom will be 9, remember n-1, and we need to find this t-score, which will be the same as the lower one. The t-distribution is symmetric. So look up row 9 of your t-table, and our alpha was 0.1, so alpha over 2 is 0.05. That's our area. Let's go check that out in our t-table. T-table gives area to the right, so we might as well go for the right-tailed here. We have n is equal to 10, so we're in row 9. And we're looking for 5%. Remember, alpha was 10%, so we want half of that. So our critical value is negative 1.833 and positive 1.833. Anything in between there is not rejected, but anything bigger than 1.833 or smaller than negative 1.72 would be rejected. Our value, though, is sort of around here. Now 0 is in the middle. So we're going to fail to reject. Step 7. Fail to reject the null hypothesis, as I thought. And then step 8, we write our conclusion. Go back and look at how we set this up. Remember, the claim was the null hypothesis, and we didn't reject it. So we're not rejecting the claim. But remember, in the fail to reject case, it will be sort of wishy-washy. We're not going to say they're right we're just going to say, we can't say they're wrong. If you don't believe me, take a look at our chart. I'll flip back. In the example we're doing right now, we have the claim is the null hypothesis, and we failed to reject it. So this will be our conclusion. There isn't enough evidence to reject this claim. There's insufficient sample evidence to warrant rejection of the claim. And that's how we'll write it up. There is insufficient sample evidence at alpha equals 0.1 anyway to reject the claim that the mean deflection of the, I don't remember, 10-meter beam or whatever they were, to reject the claim that the mean deflection is 0.150 decimeters. So that's how we handle those things. It isn't too bad. Notice how we went through these much faster now that even though this was a new test, we hadn't done a test for the mean yet. The 8 steps are still basically the same. The structure holds true regardless of what sort of test we're doing. Thought maybe we could take a quick look at the p-value using Excel, as the p-value is rather difficult to get off the t-table. So here's the same example. I pasted the values into Excel, and then I ran the descriptive statistics add-in. You can see that it gives you the confidence interval. Remember, I set it to do 90%. I think the default is 95%, but you can change it. So using this, we had our mean of 0.1417 plus or minus the confidence, and we can see that the mean should be, we're 90% confident that the mean is between 0.13 and 0.1505. Well, the claim was that it was 0.150, which is in this interval. So we would fail to reject that claim. So the confidence interval does coincide with our decision that we had doing it, the formal hypothesis test. I calculated the test statistic using Excel. Sadly, there's no built-in function. I had to actually basically manually create my own formula there. But I was able to just reference, here's where the mean is, here's where the standard deviation, here's where my sample size is in my formula. To get my p-value, I want the area then to the left of this value, and then I need to double that. So, oh, look at that. The t-distribution actually has a .2t. So I just plugged in my t-score and my degrees of freedom, and it will give you the p-value. But I noticed that when you do the 2t function, it doesn't allow you to put a negative number in for t. So I had to I just changed it to, I put an extra minus in to make it positive. And then that gives us our p-value of 11 or almost 12%. The p-value is greater than alpha, so we fail to reject the null hypothesis, and we get the same conclusion. I messed around with some other functions for p-value here. I messed around with what would it have been if I were trying to use a z distribution, pardon me, instead of the t distribution. And I also messed around with there is a t dot dist right. So I was able to find the area to the right of positive 1.72, which is half of our answer. So I doubled it there. So there is a right. We were wondering if there's a t dot dist or t dot inv. And there isn't one that goes to the right, but there is a two-tailed version. So in our case, when we did it the traditional way, our t alpha over 2, we would say t dot inv dot 2t. Our probability then was 0.1. You remember alpha was 10%, and we had 9 degrees of freedom. Oh, it didn't match. Oh, yeah, it did match. That was what we read off the table. Remember, this is our test statistic here. So using Excel is pretty handy for getting p-values, that's for sure. And it is also very handy for getting your mean and standard deviation, particularly when you have larger data sets. So I think we've basically taken care of this example. And we've talked about, now in this lecture, we did confidence intervals and hypothesis tests for single means and for single proportions. Coming up next, we'll do paired values. So we'll compare the means of two populations, and we'll compare the proportions of two populations. So we're going to do just more hypothesis testing. These 8 steps will become pretty natural after we do a few more. That's it for today. I will see you all next time.